Now, I know I said that I was going to take a break after recording the video with the weak duality theorem, and I did, and then one thing led to another, and it's actually been 5 days since that happened. But in those 5 days, the weak duality theorem made sure to eat its vegetables and take its vitamins every day, and it grew up to be big and strong. And so here we have the strong duality theorem. Now, recall, even though you probably just watched the previous video, for me it's been a while, recall that the weak duality theorem tells us that if I look at any feasible point for the dual LP, that the objective value I get will be greater than or equal to any feasible point for the primal LP. But of course, there is that question whether there will be a point where they match, whether there's going to be a gap between them. And the strong duality theorem says that there won't be. It says that you will always be able, assuming that the primal LP actually has an optimal solution, if the primal LP has an optimal solution, then so does the dual, and the objective values of each optimal solution will match. And of course, what's astounding about this result is that what this is really telling us is that if for some reason I think the primal LP is hard to solve, and I want to know that optimal objective value, then I could just solve the dual LP and get it that way. And so, of course, the strong duality theorem is a really big deal. Now, the proof that we're going to walk through here is the one from the Vanderbeek book. So just like before, with that proof that Bland's rule doesn't cycle, I am going to use the same proof that Vanderbeek gave with a few notational tweaks, both to try and ease the burden of scrubbing through all the notation, and also to make some aspects a bit easier to explain. I guess because explaining something on slides versus explaining something in a book are two different arts. It's also important to note that there are other proofs of this result, and arguably some of the other proofs might better expose some of the underlying intuition or the geometric interpretation that goes along with this. The proof that we're going to use is based on using the simplex method, which I think is a cool idea, and other than that, just a bunch of algebra. And so it is a bit of a tedious proof in that sense. I like it because I think you need to see at least one full formal proof of this theorem. And the one that I've chosen, the one in the Vanderbeek book, has the benefit of not requiring anything else. The more geometric proof that you could find in our other book requires a bunch of other results, and then proving those other results can be quite complicated, although you could take a look at that if you're interested. I think I might talk about those other results a bit, at least informally, in a live session, but as far as going through a full formal proof, we will go through the one from the Vanderbeek book. And it's interesting because I've mentioned before that some of the proofs in that book can be a bit of a drag. Like they go, lots and lots of algebra, and you sort of lose sight of the goal after a while. And it's interesting because even Vanderbeek actually mentions that in the preamble to the proof. There's a section before the proof talking about, I think, to paraphrase, he says something like, a well-written proof is important and can be valuable, but sometimes writing a proof out concisely, I guess disguises what's really going on underneath. And so Vanderbeek actually spends a few pages talking about what the proof is actually trying to establish. And what it's doing, the real intuition behind it, and I have to be careful the way I put this, the intuition behind the proof is that if I apply the simplex method to the primal dictionary and I end up at some optimal primal dictionary, using what we saw in part 1, this idea that whenever you perform an operation on the primal dictionary, you are sort of performing an implicit operation on the dual dictionary as well. It turns out that if you solve the primal LP, if you get that optimal dictionary, you will end up with an optimal dual dictionary too. Now, the reason I have to be careful is that I say that's the intuition behind the proof. I don't want to make it sound like we're assuming that that's true and that that's going to somehow drive the proof. Instead, we're going to prove that that's true sort of as a side effect of the rest of the proof. And that's great because that means that by writing this particular proof, we will be formalizing the connection between solving the primal LP with a primal dictionary and solving the dual LP with the dual dictionary. And we'll talk a little bit later about this dual simplex method, which is where you solve the dual LP directly, but you only use the primal dictionary because you can use the negative transpose property to avoid ever having to actually construct this dictionary in full. So the property that we're going to leverage primarily is this idea that in my optimal primal dictionary, I'm going to have a negative objective coefficient on everything that isn't basic. And we know by this negative transpose property that seems to apply to dictionaries, that'll mean that these values here are going to all be positive. And of course, these will be an assignment to the basic variables of the dual LP. And we know, of course, that if all the basic variables have positive values, or they're 0 or positive, then we've got a feasible solution. And it's going to basically rest on that. We're going to construct using the optimal primal dictionary, construct a particular assignment of y values, and then show that that assignment is both feasible and has the same objective value as this optimal primal objective value, which will be enough to show that it must be the optimal dual objective value. So we will be proving essentially the negative transpose property as a side effect of this. We're not assuming that it's necessarily true. We are instead using this and sort of deconstructing the optimal primal dictionary and then reconstructing it into an optimal dual solution. Okay, so fine, let's start the proof. Suppose that our primal LP has an optimal solution. So that's what the theorem was doing. The theorem doesn't cover cases where the primal LP is unbounded or infeasible, although weak duality does say a few things about about both LPs in those cases. So suppose the primal LP does have an optimal solution. We know by now that the simplex method, as long as you find some way to prevent cycling, will always find an optimal solution if one exists. So let's suppose that we ran the simplex method, and let's let P be the optimal dictionary produced by the simplex algorithm for this primal LP. What we're going to observe, strangely, is we do use the optimal objective value of the primal LP in a couple of places, but at no point do we ever actually use the assignment to optimization variables. I mean, there is implicitly in this optimal dictionary P, there is some assignment to X variables that comprises the optimal solution, but we never actually need it in this. So what we're going to do in the proof is we're going to construct this vector y star and then demonstrate that it's feasible for the dual, and also that this, which is the dual objective value for y star, is equal to the optimal primal objective value. And we know by weak duality that you couldn't get a better dual objective value than one that equals the primal objective value. That'll be sufficient, therefore, to show, if we can show this point and this point here, both of these together show that y star is indeed an optimal solution to the dual LP. Okay, so the first step. In our optimal dictionary for the primal LP, we know that the objective row will look like this, as usual. It'll be some constant, and this because it's optimal, this will be the optimal objective value, plus a linear combination of non-basic variables multiplied by objective coefficients. So the first thing we should observe is that because we define this dictionary P to be optimal, then obviously there can't be any choices for entering variables, which means the objective coefficient of every single thing in this objective row has to be less than or equal to 0. Because if any of them were positive, we would have a possible pivot. And we know that we don't define a dictionary to be optimal unless all of the objective coefficients are non-positive. Okay, so that's the first thing. And we're just going to put that one in storage for now. We'll come back to it in a few slides. The other thing we're going to do is the same trick that we did in that proof about Bland's rule, which is these summations here are somewhat elegant to stare at, but they can be quite clunky to work with if we want to do tedious summation algebra, because we have to keep worrying about what does it mean for a variable to be non-basic? How do I differentiate between basic and non-basic variables? So we're going to use the same trick that we used in the proof that Bland's rule doesn't cycle, which is we will observe that we can extend this linear combination all we want as long as we make sure that the coefficients of all the other variables are 0. So what I could do is I could extend the linear combination so that instead of just saying xj, summing over all xj that are non-basic, I could sum over all possible xj with the understanding that I define the objective coefficient for the basic variables to be 0. So that actually has no effect on the objective expansion itself. It just gives me an easy way to avoid having to keep worrying about basic and non-basic variables. I just define an objective coefficient for everything, and I assume that it equals 0 for everything that is basic. So I'm going to do that. And we are still going to keep the x's and w's separate. So in a previous proof, I would often try to find an excuse to combine them, but here we're going to keep them separate because we do care. There is a different treatment we want to give the x variables and the w variables. But in any case, we will extend this objective expansion to include all x and w variables with the understanding that their coefficients equal 0 if they are basic. Once I've done that, I end up with this. And I'm taking care in these expansions deliberately to use a different summation index for my sum over the x variables and my sum over the w variables, because I want to illustrate that they do refer to different things. So the x variables are our optimization variables, the sort of original non-basic variables from my initial dictionary, and the w variables are the slack variables. All right, so the other thing we're going to do, which is also very similar to the proof we did about Bland's rule, is we are going to make inferences about the behavior of the LP in general, about the behavior of the whole system, by comparing the structures of different dictionaries. So we know that any dictionary I come up with by starting here and performing pivots, frankly, whether or not they are feasible pivots, any dictionary I come up with expresses exactly the same set of relationships that this one does, as long as I come up with it by performing pivots like we're used to. And therefore, if I pivot a few times and I come up with some other objective expansion, I might be saying something in terms of the simplex method by doing that, but more importantly, that expansion is the same as this. It will equal the same thing. If I provide a particular assignment of x variables, then the objective value will always equal this, but it will also always equal this. And we sort of know that that's something I've brought up every time that I talk about dictionaries, this idea that performing pivots doesn't change the system of equations. It just allows you to express them in different terms. So we're going to notice that. And of course, we shouldn't be surprised that obviously this is a valid expression of the objective function. If I get to my terminal dictionary, if I find an optimal assignment, and I pull out the values of each x variable, and then I run it through this form here, I will of course get the same objective value, because this is the original expression we were trying to optimize. So what we can do, because this is an identity, is we could say, well, I found one way of expressing my objective function. This is the way in the initial dictionary. And I found another, which was the way in the optimal dictionary. And these must be equal. And I don't just mean that the value that I get by computing the sum, the constant result, I guess, is equal. What I mean is that this is an identity for any valid assignment of x values. In other words, if you give me any way of any particular assignment of values to each xj, and then you go and compute the wi for that particular assignment, because of course we know that each wi is defined in terms of the x variables. If you give me any assignment to the variables xj and then go compute the wi, this will always hold. Always. So they are equivalent, the two sides of this equation are equivalent expressions of the objective function. It doesn't just hold for the optimal x assignment, it holds for any x assignment, assuming that I compute the w's accordingly, assuming I compute the w's in keeping with the system of equations that was defined by the initial dictionary. And we'll see in a few minutes that that property is going to be very important. And we did something very similar in the proof about Bland's rule. We're actually going to apply the same basic trick, which is creating these identities that have to equal 0 for any possible real number, and then draw conclusions from that. That's a trick we used briefly in the proof about Bland's rule. We're going to use it several times in this proof. So what we're going to do here, based on this expansion, is we are going to define this vector y, and we're going to then prove that y is feasible and optimal for the dual LP. So the definition of y is actually pretty easy. What we're going to do is define each variable yi to just be the negative of the corresponding objective coefficient on my slack variables wi. And if we scroll back to this, something that we brought up in part 1 was this interesting correspondence, although we can't really say equivalence, but there is a correspondence between the slack variables of the primal LP and the optimization variables of the dual LP. And we know that the correspondence is sort of hard to flesh out completely, because there are clearly some obvious differences. The biggest one, of course, is that if a w is non-basic in the primal, the corresponding y variable will be basic in the dual LP, and that, of course, means that the w value will equal 0, while the y value may not equal 0. But there does seem to be some connection between them. What we're going to do in the proof is we're going to define each variable y to equal the negation of the coefficient on the corresponding w. And you'll notice in this example here, that is exactly what it does. And we're sort of proving this fact in a sense with the proof that we're currently writing. So I define each variable yi to just equal the negation of the coefficient on the wi, the corresponding wi in the primal LP. But of course, remember from the trick that I employed on the last slide to get from here down to here, it's possible that some of these wi are actually basic in the primal LP, but we've defined that in that case, the corresponding coefficient will just equal 0. So now we have to demonstrate that this particular choice of y is feasible and optimal for the dual LP. So the first thing we're going to do is we can reverse that relationship. So I wrote out that yi equals negative qi. Okay, well, so obviously that implies that qi equals negative yi. And we can then begin substituting in y's in place of the q's in this identity I constructed off of the objective expansion. I can also use the fact from the initial dictionary that each w formally is defined in terms of the x's. Remember that regardless of all the pivots I performed in the meantime, every w will always, so w1 will always equal this expansion here. If you give me an assignment of x values, w1 in any dictionary will always equal this, regardless of how I've transformed the system of equations in the meantime. So if I perform these two substitutions, which allows me to eliminate the q's and the w's completely from this identity, if I perform these substitutions, I get this. So the q's turn into negative yi, the w's turn into this thing. And then a bunch of algebra happens, and I'm not going to belabor that, but trust me, I mean, you can try working it out yourself. It does work out. Basically, what I want to do is manipulate the sums so that I can get a separate sum for y's and x's, essentially. So here's a sum involving only y, and I pull that out separately. That's one part, that's sort of this part here. And then I want to get only a single sum that involves x. And so what I have to do is mix together this and this, and then reverse the sort of trade orders of terms, and I end up being able to factor it so that I get this sum over from j equals 1 up to n of this thing times xj. And the key thing is, for later, it's going to be significant that I only have each xj appearing in one place. So it's tedious algebra. You can go ahead and try it if you don't believe me, but I'm not going to go over it in much more detail than that. We've spent so much time in this course rearranging sums that I think we can believe it's possible. So I end up with this. This sum, I'll just pull this sum down here. This sum ends up equaling this thing. And remember what I said earlier. This isn't just a relationship I've discovered about the optimal solution. This is a relationship that holds for any assignment of x values. I mentioned earlier that this identity holds for any assignment of x values as long as I compute the w's accordingly. But here, because of this substitution I did, this is the computation for wi. If you give me a particular assignment to x variables, this will compute wi for me. So now what I've stated, the way I've written it on this line here, is an identity for any possible assignment of x values. Okay, so I'm going to move things around, and I end up with this, equation star. So equation star says that this whole thing, this entire left-hand side, will always equal 0. No matter what values, x values I choose, this will always equal 0. That's a big deal, because we know now, because I can choose any set of x values, I could do that. I could change which x values I'm working with to try and divine more and more information about what this is really saying. Okay, so I spend a lot of time thinking about how to explain this properly. That is, I know that this is a bit nebulous, this idea that, okay, I've somehow managed to state an identity in terms of any possible assignment of x values, especially given that there's a whole bunch of other things, symbols, sitting in this equation, and we can't help but wonder why those don't factor into it. And the key thing is that, remember that everything else I have here besides the x values is a constant of some persuasion. So the bi's, for example, are part of the LP I was provided. The aij, similarly, is part of the LP I was provided. The variables yi and pj, remember that yi is actually one of these q variables in disguise. These variables are a function of also the original LP. They're the result of taking the initial dictionary and performing some sequence of pivots. But regardless of what values I have for x, if I perform that sequence of pivots, I will get these constants in the objective expansion. So they're constants. They don't depend on x. And as a result, it turns out the only thing in this entire expression that really isn't a constant, as far as we're concerned, that isn't really a function of the original LP, the only thing in there that's a variable are the assignment of x values. So that's a key thing to observe. Because of the way I've written it on this slide, it's easy to forget about that. So what I decided to do is convert this identity to a sort of functional form to make it much more clear what's a constant and what's a variable. So what I'll do is I'll define a function phi, uppercase phi, and its arguments are x1 up to xn. Just to make it really clear, the only thing that I can vary here are these assignments to the x values. And we will define phi of x1 through xn as being the left-hand side of equation star. Okay. So what equation star is actually telling us is that this function phi equals 0 for every possible input. So that's it. That's all it's really saying, is that no matter what assignment you provide of the x variables, phi always equals 0. And I think if we use that notation, if we use this functional notation, it makes the rest of the proof quite a bit easier to understand because it allows us to break it up into much more discrete pieces. Because the first one is, I know that no matter what I plug in as these arguments, the result equals 0. So I'll start by plugging in only zeros. I assign 0 to every x value. And hopefully it's clear, because of the way I factored this, if every x equals 0, this entire sum just goes to nothing. So the sum completely vanishes, and we end up with this. But that's because of what I just said, because phi has to equal 0 for all inputs. What I'm saying is that this whole thing has to equal 0. Okay, fair enough. So then if I move terms around, what I mean that is if I put this here and I move this over to this side, what I'm really saying is that the optimal primal objective value equals this sum here. And if we stare at that sum for a minute, we observe that that sum is pretty obviously b dot y. In other words, the dual objective value of this particular vector y, so b dot y, is equal to the optimal primal objective value. So that was one of the two goals that we set out to achieve, to demonstrate that assuming that this vector y is feasible for the dual LP, that it does realize the optimal primal objective value, and by the weak duality theorem, it simply can't realize a lower objective value than that. Therefore, this will be optimal if we can show that it's feasible. So what remains is to show that y, it shouldn't say y star here, we want to show that it is y star, but to show that this y that we just constructed is feasible for the dual LP. Okay, so to do that, we have to show that it satisfies the constraints of the dual LP. All right, so what we're going to do is go back to our function phi and try evaluating it with a different assignment of x variables. And this time what I'm going to do is I'm going to set x1 to equal 1 and every other x to equal 0. And what we'll notice if we go back to the way phi is actually defined on this slide, if I set every x but x1 to equal 0, then the summation ends up just having only one non-zero term, and that's the one involving x1. Okay, so I end up with this. If I just set x1 to equal 1, then I can just ignore this. What I end up with is what we see on the next slide, which is this thing. The only term that I keep is the term involving x1. And notice that what that allows us to say is, well, first, we already know that this thing here is equal to 0. We just established that on the previous slide. And that means that what I end up with is this. So phi with x1 equal to 1 and everything else equal to 0 ends up just equaling this term here, because we know that this other thing is 0. But also, phi equals 0 for any set of arguments, which means that this thing has to equal 0. And so we can do the same thing. We did this for x1, but maybe you'd buy it if I told you we can do that for any particular value j. So x1, x2, x3, x4, whatever. So I can show that for any value j, this has to equal 0. And then what we're going to do is take this apart and see if we can draw any conclusions about the behavior of y and relevant to c, because we know that each y and ai, j, and c all factor into the constraint system of the dual LP. And it turns out that we don't have to do too much. So I guess I'll use this slide to illustrate it. Really, what we want to do is talk about the relationship between Cj and yi, and this sum yi times aij. The problem is there's this other term p sitting in there, and we've got to do something with that. But we know from earlier, I mentioned this was going to come back and haunt us, we know from earlier that, let's see, where did I define this? At the very beginning of the proof, I pointed out that p is one of these objective coefficients in the expansion of the objective function in the optimal primal dictionary. And we know that every objective coefficient in the optimal primal dictionary has to be non-positive. So each p has to be less than or equal to 0. Okay, so if we bring that back over here and transplant that, if pj is less than or equal to 0, what does that tell us? Well, let's see. If we try moving terms around a little bit, let's see. The easiest way to do this. Okay, how about this? Let's try this. If I move these terms around, so I have negative cj plus the sum equals negative pj. Well, wait a minute. So pj is less than or equal to 0, which means negative pj is greater than or equal to 0, which means that negative cj plus this summation here has to be greater than or equal to 0. And that's actually all I need to establish, because if we then move things around a little bit further, so I think the next slide picks us up there, we end up with this, because pj is less than or equal to 0. So we end up with what I just had was this expression here. And if we just take cj and transplant it over to the right-hand side, we end up with this. And if you stare at this for a minute, you realize this is exactly the statement of a particular row, so row j, of the dual constraint system. And what I've said here is, therefore, that this assignment to y values, this vector y, does satisfy all of the constraints of the dual LP. And furthermore, it turns out that each yi is definitely going to be non-negative, because we know that we defined yi to be negative qi, and the qi's were objective coefficients in the optimal primal dictionary, and we know therefore that qi is less than or equal to 0. So negative qi would be greater than or equal to 0. And so what we've now managed to show is that this vector y that I just constructed by taking the objective coefficients from my optimal primal dictionary, this vector y is feasible for the dual LP, and that the dual objective value that I realize with that feasible point is equal to the primal objective value, and it can't get any smaller by weak duality. And therefore, I've been able to construct, given an optimal primal dictionary, a feasible solution to the dual LP that realizes the same objective value. And of course, that is enough to prove the theorem. Now, I'm going to take another break. Hopefully it's not 5 days this time. And then I want to talk about a couple of other implications of duality that we're going to need.